as well. Okay. So she will talk about the unique island habitats, test of the theory of island biogeography in marine and terrestrial habitats. So please give your big hand.
Thank you everybody for having me. It's such a pleasure to be here in Korea, so thank you to the organisers as well from the Australian team. So as Osio said, I'm Eleanor, I'm from Australia, and I'm going to do my presentation in two parts today. So first a little bit of discussion around the sort of career you can have in ecology, because I know that there are a lot of students here, and this meeting is about students and bringing students together and giving them some idea of what the possibilities are. Of course, this is in the Australian context, so maybe it's different in your country, but that's the only perspective I can give, so I hope it's helpful for you. So just as is customary in Australia, I'm just going to quickly acknowledge the traditional custodians of the lands on which I work and which I prepared this presentation, and also did all my studies. So that's the Yagara and Turrbal people nations of the Brisbane region, which is in Queensland. So, I apologise that it looks a little funny because I did do this in a PDF, not PowerPoint, because my presentation had too many pictures, so it didn't quite fit. So this is just a little career trajectory of what I did in my life. So I actually started with a Bachelor of Theatre. So I don't know if you guys know what theatre is, but it's like acting. So I started with arts, and I guess I'm a little bit unusual in that I'm very artsy, but also sciencey at the same time. So I love both. And I think actually having the arts background, the theatre background has been really beneficial in science for communication. So it might seem a little bit strange, but it actually works well. So then I went over to UQ, the University of Queensland in Brisbane, and I did botany and ecology. Following that, I'm sure in your countries there are plenty of jobs in the government doing environmental regulation and policy. So I did that for about 10 years. And then I left and I did a PhD in community ecology at the Queensland University of Technology. So I think the message I wanted to send you is, it's never too late to try something new. It's good to try new things at different times in your life. And it's something that I think has been really joyful in learning new things at different stages in life, based on your interests, right? And so then I worked as a lecturer for 4 years at QUT, Queensland University of Technology, and also Griffith University. So I taught a lot of undergraduate students, master's students, and I have one of my own PhD students there. And then I did my Masters of Education. Another study. But I guess I fell in love with teaching. When I was at Griffith lecturing, I just found that teaching was just the best thing. I love working with students. And I think it's just a good thing in life to just pursue the things that you love. It makes you happy, right? And then, now, I work at TURN Australia. So TURN is similar to the Long-Term Ecological Research Network. We form part of that community internationally. And my role there is trying to make our data, so we're essentially a giant data repository, to try and make that data a little bit more accessible and useful for both governments, but also for students, because we would like students to use our data in their undergraduate courses. So I'm trying to bridge that divide. So that's just a little bit of, for interest's sake, things that you can do in ecology, different paths you can take. So this is part one of my presentation. It's a little bit of my own research that I've done that I think you might find interesting, and feel free to ask me about it later. But what I have done is I tested the theory of island biogeography in 2 different island-like habitats. So it was a modern test, and I'm going to explore what the differences are, but just while we've got these photos up, the first system that I tested the theory in was a marine system of floating pumice rafts in the Pacific Ocean. So the cool thing about these rafts is that they get colonized by basically everything you can think of that lives on a shallow marine ecosystem. So corals, anemones, barnacles, bristleworms, everything that you can think of. So it's a really unique way of testing that theory. And then I also looked at a critically endangered species of Melaleuca. Melaleuca urbiana occurs in Brisbane, and it's critically endangered. I think it's only got about 8% of its original distribution remaining, so it's highly endangered, and farmers don't like it very much. They like to clear it, so it's a bit of a challenge in the policy and social space. So, I don't know, I know some of you are non-ecologists, so a little bit of a theory lesson. So the theory of island biogeography is a theory in ecology that was originally conceptualized in 1963 by MacArthur and Wilson. And they raced against the time to get that theory out there because a lot of people were thinking along the same lines at this point in time. And the book was published in 1967. Now, it still remains, all this time later, a fundamental theory in ecology because it is one of the only theories, I think it's the only theory that has been tested and proven on multiple times. So there's papers about it that have proven it pretty well to a certain point. I don't think it's as good as, the theory of relativity or the theory of gravitational pull, but it's still pretty good for our discipline. So that's that little bit of theory, and this is the main equation of that theory. So just to walk you through that, you've got the rate and change of species in a new habitat. So if you think of a volcano erupting, say, in the Pacific Ocean, and it forms a new island, that originally that island's going to have no species on it. And through time, species will start colonizing and migrating to that island. And then, as the number of species goes up, so on this trajectory, we've got the extinction of species and the immigration of new species. And then at some point in that island's, ontology, which is a fancy way of saying through time, they'll eventually meet in the middle. And so the number of extinctions will stay the same as the number of immigrations. No more new species are coming. They're still coming, they're just not coming as new species. So that's called the dynamic equilibrium. So, I'm just going to skip over this. I'm going to tell you the ones that I think are the most important, so you can just listen to me tell a story if you like. So the main relationship that underpins all of this theory is the species-area relationship. Hands up if you've heard of the species-area relationship. Yeah? Okay, so I'll tell you a little bit about it. So the basic premise of the species-area relationship is that if you have a larger habitat, you've got more space, right? So then you can have, what do you think? More species, right? So you can have more species, that's the theory. And then if you have a smaller habitat, coincidentally, you've got less species, you don't have as much habitat. Simple as that. It's a super simple theory, and I think that's why it's a pretty interesting theory, but also useful theory to test. And it's evolved. So in 2008, a really amazing scientist, I think he works at Oxford, he's amazing, I met him when I did a conference in Germany. He added to this theory. So he added different predictors, so not just space, but he also looked at time, age, and I added a little bit into my PhD with the factors of habitat disturbance. Okay, so I looked at fire, because we have a lot of fire in Australia, okay? I don't think you guys have, do you guys have much fire in Korea? I love talking to my audience, by the way. Who has lots of fires in their home country? Thailand? Taiwan? Mongolia? I'm trying to remember where everyone's from. I'm doing a bad job. Okay, cool. Alright, so let's move on because I'll probably run out of time because I like telling stories. So these are my two study systems. already talked to you about that. I'm going to skip over that. So let's go into pumice rafting. So in 2012, this giant caldera, which occurs in the Pacific Ocean, just off the coast of New Zealand, erupted. It hadn't erupted for many, many years. They thought it was extinct, completely dormant, totally unexpected, and very lucky that it wasn't near any populations. It was in the middle of the ocean. And the first person to see it, funnily enough, was taking a flight from Australia to New Zealand. And they saw this giant thing floating in the ocean. It's a cool story. So anyway, the pumice raft, if you can imagine what pumice is, who knows what pumice stone is? We actually saw a little bit of geological stone yesterday. Did you see the stones in the national park that have little bubbles and air holes in them? Yes. So if you have enough bubbles and air holes in your volcanic rock, it can float on the surface of the water, because it's really light, okay? And this pumice raft, which was floating on the top of the water, contained 4 trillion pieces and was the size of France in surface area. So this is an image from NASA that shows you the size of the pumice raft. And this is where it erupted. So it just started floating through the ocean like that. Now, if you can imagine, as it floats through the ocean, all of these tiny little zooplankton and phytoplankton start colonizing it. So then it ends up about a year later arriving on the shoreline of Australia, and you have this perfect test of the species-area relationship and the theory of biogeography, because you can look at how many species have colonized each piece of pumice in relation to its area and how long it's been floating. Because you know that it started floating on a specific date because we have satellite imagery. So that's the wonder of modern science. So we were able to publish this paper, which showed that age and area did predict the number of species floating on the pumice raft, the little individual pieces of pumice. And that's just a picture of, I don't think this is the volcano that I studied, but it's another one. Because if you know New Zealand, I don't know if you've heard of New Zealand, but it's just like a huge country to the east of Australia. It's highly volcanic, and they have so many volcanoes, and those volcanoes extend under the water for lots and lots of kilometres, and it's called the Climatic Arc. I took out the map because I felt like I didn't have enough time, and I'm sure I'm going to have to be stopped before I finish. So this is just a little bit of the statistics that we found. I used a statistical model called mixed effects models. It's basically where you are able to use the statistics to put multiple linear regressions through your data and test which predictor has the most power in comparison to the other one, all at the same time. So it's a fantastic way of modelling in ecology. I love it, and it's pretty simple, so it's not too hard to do if you're in your master's or PhD. So this is just a little bit of what I said before. Older pumice class, so the longer they floated through the water, had more species, and then larger pumice class. So it was a combination of time and area. And this change depended on the trajectory. So if you had pumice class, they all arrived, and when the volcano erupted in the subtropical temperate zone, but some of them floated through tropical waters and some of them floated through more temperate waters, and that changed the result. So if we see here, we actually have pumice class arriving in Tasmania, and the ones that floated through Tasmania is a little island south of Australia, and they lost species richness. And we theorise that they lost that richness because they were floating through cooler waters that tropical species couldn't stand. So subtropical and tropical species started to die off. Tropical and subtropical species had positive slopes, although there is a bit of a wide error margin here. So that's just the results there. Hope that made sense. The next one is, remember I was telling you about the critically endangered forest that I studied. So again, we have an island-like habitat. So this is a habitat that's been extensively cleared, and there are farms and houses all around these little tiny pockets of forest where this tree still exists. And it's called Melaleuca urbiana. It's a beautiful tree. Oops, sorry, I went the wrong way. So it's critically endangered, and only 8% of its ecosystem remains, so about 1,000 hectares, so it's so tiny. And it was a naturally rare species to begin with, so it grows in a pretty specific habitat area. Very, very hard soil. It's like concrete. It's a cracking clay. Yes. So the reserve managers, one of the reasons why we did this project, we got a small grant from one of the councils in Brisbane because they were worried that the tree was actually going towards extinction because no seedlings, very few seedlings were being observed. So these are the types of questions we wanted to try and see what that was influencing how Melaleuca obiana is growing or not growing. So disturbance factors like fire and flood, because it's on a floodplain. Is there a light problem because fires have been suppressed in those reserves? And we all know that seedlings growing underneath big trees need light to emerge and grow, right? And then reserve size, how far away from each other the different reserves are, and what sort of overstory or understory species there are. So are there lots of weeds in the reserves suppressing growth, things like that. So I surveyed with a team of amazing volunteers. They worked so hard, it was very hot. 4,000 overstory trees, and we found 254 seedlings. So there was still some hope for this tree, which is good. The interesting thing, and this is because this is a highly fragmented ecosystem, is that area and isolation did not really explain what was happening in those ecosystems. However, there was an increase in native understory species. And the most interesting thing, I think, was that fire seemed to be a good predictor of seedling recruitment. So this tree we don't know very much about this tree in terms of how seeds germinate, but it looks like fire actually helps it to regrow. So that was, that's that part of the presentation. I'm going to jump into part 2. I think I've got like 10 minutes left, so let's do that. Okay, so this is what I do now. So as I mentioned in the beginning of my presentation, I work at Turn Australia now, so it's a little bit less research intensive. I don't do as much teaching, but I do work in education, and I'm trying to think of all the ways we can excite young ecologists to come into the long-term ecological monitoring space. And also just to, I guess, influence the general public and influence society to understand why science matters and why ecology matters. Because these are the things that are going to help us, combat climate change, food insecurity, all of these wicked problems. So, I don't know if many of you have heard of Turn Australia. I know some of you have, but has any of your students heard of Turn Australia? Not too many, you guys have. So I will talk about that a little bit. So what we're trying to do is advance ecosystem science and contribute to the sustainable management of Australia's environment. And we want to aid and help governments and environmental managers to make sure that we don't degrade our ecology and our natural systems further, because we're all having an influence on the planet, and this will help us solve the wicked problems of our time. So we all know that environmental challenges are global, and that's why Turn is really a network of networks. We bring a lot of people together, and I think this is a part of the philosophy of this ecology school as well, is bringing people together. Because we want to be able to help each other to work with these really wicked problems that, are kind of our own making. Climate change, global warming, food insecurity, more pandemics, all that kind of thing. So Turn is Australia's largest ecosystem observatory. I stopped myself then because I was going to say terrestrial, but we're actually adding in coasts now. So we're looking at mangroves and I guess sandy shorelines and rocky shorelines as well. So we do it at the continental scale. So where and when is change occurring with satellites and drones and things like that. What and how is changing. Can't see my slide. So that's the regional scale monitoring. And then why is change occurring. So we have very fancy instrumentation. It costs a lot of money. Constantly sending us data. So we're a giant data repository. And I think the thing that I see as really important to my role in education is helping people to access and use that data in better ways. And I think that's it's going to be all about the data. It's already all about the data. And I think as we go further into these wicked problems, the data is going to just become even more important. Can I play a video? So it's going to be more of me talking, but it basically gives you a good idea of what Turn does in a beautiful way. Thank you. I don't know if we can hear it. Sorry, hear it. Sorry about the ad, guys. Hopefully it's a good ad.
Yep. It's what?
24/7, 365 days a year. Hello, I'm Dr. Eleanor VELASQUEZ. Across the continent, Turn's people and instruments are measuring ecosystem changes, from below the ground to high above the canopy. Field crews survey 900 Turn sites in key biomes and collect plant and soil specimens. Satellite and airborne imagery records the trend in site and landscape changes. On-ground sensors monitor biodiversity, long-term changes in soil, carbon, energy flows, and water. Turn's collections, as well as its data from sensors, satellites, and field surveys, are openly available to scientists everywhere. Considered together, Turn's big and small measurements have an important story to tell about the changing health of our overall environment.
Thank you. She says it better than me. So this is a wrap of all the Turn sites. Oops, sorry. Where's Payne again? Yeah, YouTube's still going. Okay, so this is a map of all the Turn sites in Australia. So we have more than 1,000 long-term monitoring sites across the continent. And I don't really know how to explain this, but Australia's huge. Who's been to Australia? I'm looking at people who've been. It's massive. So, how long does it take to fly from Brisbane to Perth? 9 hours or something? Imagine that. It's a 9-hour flight just to get from one side of the country to the other. It's absolutely enormous. So we are doing our best, but it's a lot of work. And our field teams stay out in the field for 6 to 9 months of the year with little breaks in between. They come back very tired. So this is what we're trying to do, and we do it regardless of the ecosystem or the land use management. So farms, anywhere, we need to know how the environment is changing, and we don't consider a fence line to be a boundary as long as we have permission. So, sorry, this is a little bit of a boring slide, but I thought it was really relevant to this meeting and this gathering because I really wanted to, I've been thinking about this a lot this week. How can we ensure the longevity of long-term ecological projects and monitoring? So, I sort of touched on this a little bit before, but I think repetition is always a good idea when we're talking about new topics. So, creation of educational resources, outreach products for a broad range of audiences. So the general public, we need to bring them along on this journey. We need to get in there at early ages, so students in primary school, high school and university. And then of course researchers and academics. We want them to be able to use our products easily and know that we have these incredible data sets available online for anyone to use. The education strategy value proposition is to attract and retain students. So this is where I come in and do most of my work. To attract and retain students and also encourage and inspire the next generation of long-term ecological researchers. So ways we can do this is by better explaining our science and findings to the general population and government and funding agencies, of course, because we need to keep securing that funding. So in Australia, we have to re-secure Turn's funding every 5 years. And that takes a lot of work. My director, Beryl, back in Brisbane, is constantly working tirelessly to write the best grants so she can keep Turn running for the long term. And then we want to keep the data useful for all of our key stakeholders and end users. And there's a bit of a gap there right now, but I hope there's so much work we can do in this space, so it's kind of exciting. And I'm really positive and hopeful for what we can achieve. Doesn't want to go to the next slide. Thank you. So I think I've got 5 minutes left. Oh my gosh, excellent. So one of the outreach projects that I recently launched as part of my role as Education Manager at Turn was the Engaging Science Trail and Surf Showcase event at Queensland University of Technology's Perry Open site. And some of the wonderful Korean team came out early this year and have had a look at that site a few times. So what we did, we had this initial idea to create an engaging science trail out there to try and bring in a bit more of the general public, but it's also a site that is heavily used by the Queensland University of Technology for teaching their undergraduate ecology and environmental science subjects. So, I applied to the Department of Environment, I cut off there, and Science, and they've changed their name again recently, so anyway, you don't need to know about that, for funding, and I got the grant. So I got a really small grant to start the project and kick off this initiative, so that was really exciting. So then came the hard work, of course. But this is a little bit about the site. So it is one of 16 termed super sites. So a super site is where we have all of our really amazing equipment constantly monitoring the environment 365 days a year, 24/7. We collect a range of environmental data, and it's been running at that site since 2010. So, next slide. If you haven't been to Australia, we have a really dominant tree species called a eucalyptus. Hopefully some of you may have smelt eucalyptus soil. It's beautiful when you're sick. You put it into a vaporizer, it makes you feel really amazing. And it's a gorgeous tree, and it's highly flammable. So it's part of the reason, one of the ecological adaptations to fire that Australia has, because we're a very hot, dry continent. But also, it's just a great tree. I love it. It's everywhere though. So it's actually this ecosystem, because it's in a low-lying area. We've got how many more minutes? 2 minutes. Perfect. 3 minutes. Excellent. Thank you. It's extensively cleared, so people like to live there and farm in those areas because it's nice and flat and easy to work with. So these are the things that we monitor at this site. So vegetation, composition, structure, all of the things that you would normally manage and monitor in a site like that. I'll just quickly skip over that. And these are some of the cute animals that we also look for. So I'll just let you look at that for a minute. We've got wallabies, finches, beautiful invertebrates as well. Sorry, I'm going to quickly go because I'm running out of time. So we launched the trail on June 4th this year, and we had commenced the trail walk day with a bird walk by Professor Hugh Bossingham. That was wonderful, but it was really cold. It was 7 degrees. I guess it's not as cold as you get in winter in Korea, but we were feeling it. And then we had Queensland's chief scientist come and officially open the trail. And we had 77 people come, which was fabulous. And we got them to fill out a survey on what they thought about scientific content and the trail in general. And then we had a mini conference where 16 academics showcased their research from the site, which was fabulous. And we even got to look at drones and really cool things like that. So this is just a picture of the trail. This is just a little bit of a pretend that you're in Brisbane with me walking the trail moment. So this is the entrance to the trail into the beautiful eucalyptus forest. And there's 2 of my colleagues there walking the trail for the first time. And it's a bit hard for you to relate to this, I guess, but this is how the trail looks, aerial shot. And we have 12 signs on the trail. So what we did was we made 12 signs, and each sign has a scannable QR code that then leads you to a website for the trail which has educational videos and information. And we're still working on that. I do have a video here, but I probably ran out of time for that, so I'll just skip over that. If you want to see it, you can come and ask me later. And this is just a zoomed in picture of what the signs look like. So each sign has a dedicated spot in the trail, and it is relevant to the research that is being performed in that position of the trail. So we have a soil pit there where we show people the different soil layers, etc. And we do acoustic monitoring, which is very cool too. And the beautiful scientists let us video them as our superstars for that purpose. I'll skip over that. And this is another exciting thing I just wanted to quickly mention, because I think it's a really interesting way of getting scientific information out there and public outreach. So I'm actually partnering and I've written 2 grants with a visual artist from QT. Now remember I said in the beginning I'm a bit arty. So I've also got into art school and I did theatre, so I like both science art. And he does amazing work with LiDAR, turning them into artworks which have actually been sold to galleries. So this one is called A Common Thread, and it's actually owned by a very prestigious gallery in Barcelona, so I can't play it for you. You have to go to Barcelona. An excuse. But I think it's a really unusual and unique way of getting our message across. So I just think too, in terms of careers and where you can do and what you can do, the sky is, it's blue sky situation. You never know what you will end up doing and working on. It's very exciting. It's in a very exciting space to work in. And I hope you feel inspired by this week in Korea. I know I certainly am. And thank you so much for my presentation.